A misplaced measurement could invalidate a sacrifice. A wrong proportion could dishonor kings and gods alike. Centuries before Pythagoras, Baudhayana recorded geometric principles in the Shulba Sutras. And if mathematical history has been told as a global story, his name would not have sounded so unfamiliar today. I'm Sarvajeet and you are India's Golden Age podcast. Subscribe now. The Shulba Sutra were not written for philosophers, debating in a debate hall. They were field manuals for constructing Vedic fire altars, the chithis. Every fire altar was of a different shape, meant for a different purpose, like destroying enemy, obtaining land, or prosperity. In the Vedas, it is stated that he who desires heaven is to construct a fire altar in the form of a falcon. All the shapes in chithi should be of equal area. For example, the Treta Agni consists of three shapes: rectangle, circle, and semicircle. The areas of these shapes should be equal. Shulba means rope or cord. The mathematics and measuring instrument shared the same word because geometry in ancient India never felt separate from physical practice. You learned it with your hands, kneeling in the grass, pulling cords tight against the wooden pegs. And the problems these priests were solving were astonishingly complex. Imagine being told to build a fire altar or a chithi shaped like a falcon in flight. A fire altar should be 5 layers high, built from roughly 10,000 bricks. Yet the total area has to be the same, exactly 7.5 square purusha. This was not architecture alone, it was ritual precision tied to cosmic order. Every fire altar had a different shape and a different purpose. Baudhayana tells his apprentice,
The altars must have the same area. Now think carefully. How do you convert this falcon into a square of same area?
The question sounds simple, but that is what makes it dangerous. To solve these complex problems, Vedic ritualists had to work with the square root of 2, and Baudhayana's approximation was quite precise, and we'll get to that later. His daughter watches as Baudhayana kneels besides the marked ground. He says,
Take the rope, stretch it across the diagonal. The area it makes is exactly what the horizontal and vertical sides make together.
What we write today as a squared plus b squared equals c squared, that is what he said in Sanskrit to a girl around 800 before Common Era. The chanting had begun when Baudhayana noticed the defects, and then he saw the rear portion. A few defects, not glaring ones, and yet enough to distort the sacred proportions of the entire structure. Baudhayana freezes a moment. He says,
How did this happen? I measured it myself.
He immediately proceeds to rectify the defect while the priests continue chanting around him. This is where geometry fused with rituals in ancient India, not an abstract theorem written on parchment, but a practical discipline tied to precision, transformation, and cosmic order. And here is the historical sequence that matters. In the Plimpton 322, a Babylonian clay tablet, there is a record of Pythagorean triples in 1800 before Common Era. Problem 79 in the Rhind papyrus of Egypt, dating to 1550 before Common Era, references the 3:4:5 ratio, which demonstrates a fundamental understanding of the principle. The Indian Shulba Sutras stated the geometric principle generally by around 800 before Common Era. Indian priests used ratios such as 3:4:5 and 5:12:13 because they worked reliably in the field where accuracy mattered more than elegance. The Greek formalization came afterward. Babylonians and Egyptians followed by Indians. So why call it Pythagorean? That is a different question. The answer of that is not mathematical. It is partly political and partly how textbooks are written. Centuries after Baudhayana, the Kerala mathematical tradition would follow these ideas even further. In 16th century Kerala, the Yukti Bhasha presented detailed mathematical reasoning and geometric proofs with the most remarkable sophistication. That matters, not because India invented everything, it did not, but because mathematical history was never a clean road running from Greece into Europe with the rest of the world just watching from outside like spectators. Baudhayana's approximation for square root of 2 shows how advanced Indian early geometric tradition already was. He describes a step-by-step method. Increase the measure by its third, then that third again by its fourth, less the 34th part of that fourth. The answer he arrives at 1.4142156. The actual value 1.4142135. 4 digits of precision in 800 before Common Era with no calculator, just a god. And then comes the most remarkable part. Baudhayana does not pretend that the calculation is exact. He says
saa-vishesha. With remainder, it does not end.
it took courage from Baudhayana to admit that the calculation remains incomplete. Most scholars prefer certainty. They want their measurements exact and their conclusions settled. Baudhayana leaves room for the remainder. Indian temple builders continued using rope geometry for centuries, laying out towers of temples with careful proportion. Across South India, geometric column patterns still appear before sunrise each morning, drawn by women from memory learned over many generations. The Kerala school would eventually push these ideas even further. Their work on infinite series, completed centuries before calculus emerged formally in Europe, explored a profound mathematical insight that some truths are never reached absolutely, only approached through finer and finer approximation. Perhaps that's the real story of the chord, not certainty, but precision with humility. This has been India's Golden Age podcast. I am Sarvajeet. Subscribe and share and explore India's first Golden Age further. My novel Devi is coming, a story of a queen who made Chandragupta. And we'll visit a new topic in the next episode. Till then, remain curious and bye for now and Jai Hind.